Alrighty, in this video we are going to be talking about vertical and horizontal asymptotes using limits as our justifications. So, remember how with a vertical asymptote, that's whenever our denominator is equal to 0. So what we are going to do with that is look at that vertical asymptote from the left side and see whether it approaches positive infinity or negative infinity, and then look at the limit from the right side and see if it approaches positive infinity or negative infinity there. So we'll probably pick a small number to the left of C and then a small number to the right of C and see where that gives us. Same thing with our horizontal asymptote. This one right here, we are going to see what happens whenever x approaches negative infinity, and then we are going to see what happens whenever x approaches positive infinity with our horizontal asymptotes. All right, so looking at number 10, you'll notice that we have a vertical asymptote at x is equal to 2. Great. But then what we are going to do here is justify what's happening at 2 from the left and then 2 to the right. So looking at this, we could say 1.999. So if I were to evaluate 1.999, I'm going to have 1.999, which is a positive number, over a very small negative number, which means that this right here, a positive over a very small negative, is going to be a negative infinity. So as the limit of x approaches 2 from the left of f of x, that is going to approach negative infinity right there. Likewise, 2 from the right side, I'm going to pick something to the right of 2, let's say 2.0001. So then I'm going to do 2.001. So that's going to be a positive number over a very small positive number here. So a positive over a very small positive is going to give us a positive infinity. So this tells me that as x approaches 2 from the right, for f of x, this is going to approach positive infinity here. And then we have our horizontal asymptote. So this one right here, we are going to look at what's happening as x approaches negative infinity, and then what happens whenever x approaches positive infinity. Now for this one, you might look at this and think about how this is a rational function. So we could just look at the degree of the numerator and the denominator, which you can, which is essentially 1. Sometimes that might not work with rational functions. Or let me rephrase that. Sometimes that might not work whenever you have something like a square root function here. So you'll see on number 12 what happens there. But here, if I were to substitute a negative infinity here, negative infinity over negative infinity minus 2, so negative over negative gives us a positive 1. Same thing here, a positive infinity over a positive infinity is going to give me a positive 1 right here. So this tells me that I have a vertical asymptote at x is equal to 2 and a horizontal asymptote at y is equal to 1. We're going to do the same thing for number 11 here, where we have a vertical asymptote at x is equal to 3 and at x is equal to negative 3. Which means that we are going to have to write our notation 4 times. So we are going to do the limit as x approaches 3 from the left, negative 3 from the left, 3 from the right, and then negative 3 from the right, and see what happens there. So from 3 to the left, I'm going to say something like 2.999. 3 times 2.999 is a positive number over 2.999 minus 3, which means that I'm going to have a small negative number. And then 2.999 plus 3 gives me a positive number. A positive over a negative is going to give me a negative. So this right here is going to approach negative infinity. So as x approaches 3 from the left, I'm going to have negative infinity. If I do 3 from the right, I'm going to pick, let's say, 3.0001. 3 times 3.001 is going to give me a positive over 3.001, so that's going to be a positive right here. And this is also going to be a positive, which means that this right here is going to approach positive infinity. All right. For negative 3 from the left, I'm going to pick, let's say, negative 3.001. Now, for 3 to the left and 3 from the right, what I did was plug it in into x plus 3 and x minus 3. However, it might be a little bit easier for you guys to plug it in into the original right here, because then I'm going to have a negative, and then I'm going to have something slightly bigger than 9 right here. So slightly bigger than 9 minus 9 means I'm going to have a very small positive number, which means that negative 3 from the left is going to give me negative infinity. And then what's going to happen here is if I do negative 3 from the right, I'm going to pick something like negative 2.999. So negative 2.999 means I'm going to have a negative. And then here, this means that I'm going to be slightly smaller than 9. So let's say like 8.9999 minus 9, which gives me a negative right here. A negative over a very small negative is going to be a positive. So this tells me that as I approach negative 3 from the right, I'm going to have positive infinity. And then if I were to look at my horizontal asymptote here, because this is technically a rational function, this is going to be y is equal to 0. Since we could look at our relative growth rate and see that x squared is going to grow faster than x, which means that eventually this function right here is going to approach 0 from the left side and the right side of this lovely function right here. How do we justify that? Well, we could say that as the limit as x approaches negative infinity of g of x, that's going to be 0. And then this lovely thing right here is also going to be 0. Now, on your test, you might be expected to roughly sketch this using your intercepts and all of that good stuff. So right here, I am going to roughly sketch. We have negative 3 right here, and then we have positive 3 right here. Let's see. And we also know that this is going to approach 0 as x approaches negative infinity or positive infinity. Now, 3 from the left, we are going negative infinity. So that means that it looks like this right here. 3 from the right, we are approaching positive infinity. So it's going to look something like this right here. 3 from the left, we have negative infinity. So that looks like this right here. And then 3 to the right is positive infinity. So it's going to look something like this right here. Now, why does that make sense? In other words, why did I not, let's say, do this right here? Or some other weird thing. If you look at the y-intercept here, you'll notice that your y-intercept is going to be 1/9, which means that it should be right here, which means that it should probably pass through the y-intercept, which means our graph looks something like that right there. All right, looking at number 12 now, what we're going to do is look at my horizontal asymptotes. You'll probably notice that I do not have vertical asymptotes because if I set this equal to 0, this will never be 0 right here. So there's no vertical asymptotes. Now, if I were to look at my horizontal asymptotes, though, this is where it's going to be very important for us to actually evaluate negative infinity and positive infinity here. Because you'll realize that if I were to evaluate negative infinity, this tells me that I'm going to have a negative number over a positive number, because no matter what, this needs to be positive. So this tells me that this is going to be a negative number. Same thing here. If I were to do a positive infinity over a positive infinity, so a positive number over a positive number, this is going to be a positive number right here. Now, to figure out what that number is, don't forget that we could probably compare this with x over the absolute value of x squared. Now remember that the square root of x squared is the absolute value of x. So whenever I do this, I have this little thing that I'm comparing it to. Now, if I'm approaching negative infinity here, this is just going to be a positive x over x. So that's just going to be 1, or in this case, -1. And then same thing here, this is going to be a positive 1 also, whenever I do positive infinity right here. So we have negative infinity. If I were to do that, I'll have negative infinity. So a negative number over a positive number is going to give me a -1. And then a positive number over a positive number is also going to give me 1 right there. So your two horizontal asymptotes are going to be y is equal to 1 and y is equal to 1. So it should look like inverse tangent whenever you graph it. Kind of something like that. All right, same thing for number 13 here. If I were to look at my horizontal asymptote, this is going to be y is equal to 0. If I were to substitute a negative infinity, I'm going to have 1 over negative infinity square, which means I'm going to have 1 over a very big number, which means that this is going to approach 0. Same thing with positive infinity. This is also going to approach 0 right here. If I were to look at my vertical asymptote, this is going to be at x is equal to 0. And we are going to justify y at 0, looking at the left and looking at the right. So once again, I plug in a number to the left of 0 and to the right of 0. If I were to plug in, let's say, negative 0.0001, I'm going to have 1 over negative 0.0001 square, which means I'm going to have 1 over a very small positive number, which means that this is going to be positive infinity. If I were to do the same thing with 0.0001, I'm going to have 1 over a very small positive number, which means that this is going to be positive infinity there. All right. So looking at these next couple of problems, what we are going to do here is just basically look at relative growth rates if we have horizontal asymptotes, or plug in a value to the left or to the right of the vertical asymptote. All right, so if I were to look at number 14 here, what I'm going to do is probably think about rewriting this so that I have the limit as x approaches negative infinity over 1 minus cosine of x over x. Now, here's the problem. We do not know this thing right here, right? The limit of cosine of x over x. You know the limit of 1 minus cosine of x over x, and you know the limit of sine of x over x, but that's whenever we are approaching 0. Notice how here we are approaching negative infinity and not 0, so we need to think about what's happening as this is approaching negative infinity. Now, if I were to think about cosine, remember that cosine is bounded from -1 to 1. And then I have x. So this is going to tell me that whenever I'm bounded from -1, 1 over a very small negative number, this right here, cosine of x over x, is going to approach 0. So this tells me that the limit as x approaches negative infinity of this lovely thing, this is going to approach 1. Because this right here is going to approach 0. All right, same thing for number 16 here, where what we're going to do is probably compare this with negative 3x over the square root of x squared. And remember that the square root of x squared is the same thing as the absolute value of x. So now I have this lovely thing right here. Whenever I substitute n negative infinity, I'm going to have -3 times a negative infinity, which means that this is going to be positive, over the absolute value of negative infinity, which is going to be positive. So this is going to be a positive. And then looking at my coefficients here, you'll notice that because I have a coefficient of 3, this lovely thing is going to approach +3. All right. Let's see, 21 and 23. If I were to number 21, I'm going to plug in a value that's to the left of 1. So let's say 0.9999. But I'm going to square it, so it's going to be positive, but it's going to be a very small positive number. So 1 over a very small positive number is going to approach positive infinity. Likewise, for 23, I'm going to plug in a number to the left of 1. Like I said, 0.9999. So then I'm going to have 2.9999 over a very small positive number. So 2.9999, or essentially 3 over a very small positive number is going to give me positive infinity. All right, looking at number 24 here, if I were to do the limit as x approaches 1/2 of x squared times tangent of pi x, one thing to note here is that if I were to substitute in 1/2, I'm going to get 1/4 tangent pi over 2. Now, the problem with this is that pi over 2 is undefined. Now, another thing to note is, remember how a tangent function looks like this right here. So if I'm going to look at x is equal to 1/2, notice how as I approach 1/2 from the left and 1/2 from the right, that they're not the same value. So this one is going to be does not exist because we have a vertical asymptote. Now, if this was 1/2 to the left, we'll have an answer that's actually positive infinity. Or if it's 1/2 to the right, then we'll have an answer that's going to be negative infinity. But because my left side limit and right side limit does not equal, 24 does not exist. All right, for number 25, we want to evaluate the limit as x approaches 0 of 2 plus x over cotangent of x. Now remember that cotangent of x is essentially the same thing as tangent because cotangent is at the bottom. And then I'm going to evaluate this. So if I were to use direct substitution, I'm going to get 0 plus 2, which is 2. Then tangent of 0 is 0, which is 0 right here. Now, unlike the other ones, we could use direct substitution here. It's not going to give us 0 over 0. It's not going to give us an indeterminate form. We have 2 times 0, which is an actual answer of 0. All right, so you should be able to do the rest of the problems in terms of vertical and horizontal asymptotes. Be sure, what's happening here. So for number 21, this is saying that, hey, we have a vertical asymptote at x is equal to 1. Or looking at, let's say, number 14 and 15 here. 14, this is saying that we have a horizontal asymptote at y is equal to 1. Or 15 here, we have a horizontal asymptote at y is equal to some number. Same thing with 16. We have a horizontal asymptote at y is equal to 3. And then same thing for number 17. We have a horizontal asymptote at so and so.